Let's talk about confidence intervals for mean responses. So let's suppose that we fix some x values in advance. Maybe I plan to, evaluate, observe the response at some of these values, x4, x6, okay, and you observe the response, thusly, okay, and the idea is you want to predict the average response, right? If you conditioning on observing a value of the independent variable down here, maybe at this mark, you want to know, essentially where is the average value, right? Remember, our model says that these responses are conditionally normal given the value of the independent variable, and you want to predict where this mean is. Okay, now this regression line is, maybe it's going through that way. You don't know exactly where the true mean is. If I'm here, for instance, where is the true mean of that conditional distribution? I don't know. So we want to make a confidence interval for it. Okay. Of course, if you took some data at these points, you may get a point pattern like this, and you get a regression line that goes like that. If you came along here again and took another, set of observations, here in green, it's possible that you might get a regression line then that sort of runs through that way. Okay, so these regression lines, it's important to remember the regression lines that you get are functions of your random data set. So these regression lines are in fact random elements. Okay, they if your friend does one with the same independent variable values down here, you may get one that runs through that way, or that way, or that way. Okay, so maybe you're interested in obtaining a confidence interval for the predicted response YH. Okay, H is just an index here that here. That's what it means here. H for here. Here. Okay, it's just a special mark. Okay, like this would be XH. Okay, so you're interested in predicting the response based on the fact that the explanatory variable is here. Okay, so it turns out that YH hat, the value, your predicted response on the regression line, the fit there it's a random variable, right? Because it depends on what regression line you actually get. It behaves according to a normal distribution. Big surprise. With mean given by this, right? And the variance of the YH hat, again conditioned on the value of the explanatory variable being here, turns out to be all this stuff. Okay, remember this guy's our common error variance plus 1 over n times all of this stuff. This XH, remember this is our special value here, minus the mean of all the x's squared, so it's squared deviation divided by the sum of the squared deviations of the x values. Now, notice this sum down here, however, does not include the square deviation around that h value, around that special value. This is the sum of squares for the x coordinates of the actual data values. Okay, and notice, of course, that what happens is as n goes to infinity, this term goes to 0. Okay, as before, So we used MSE to estimate the common error variance, okay? And so that's what we'll do again here. So our estimate for the conditional variance for the response here at that, for the mean response at that point then, will be MSE times all of this stuff. Notice that if you set x equal to 0 in this variance expression above, you get the variance of b naught. Right, if that is, if xh is equal to 0, then you get the variance of the expression for the variance that we know to be for the intercept term. Okay, so now I'm going to standardize this guy, this y hat h minus. I'm going to standardize it according to its mean and its variance, or rather, its our expression for the estimate of the variance. Okay, and turns out that has a t-distribution with n minus 2 degrees of freedom. So right away, this tells us exactly how to write down a confidence interval for our mean response. Okay, you take your best guess estimate for it, which is it's just the fitted value here. So you know, if this red line is your regression line, then you if you're interested in making a confidence interval for the mean response there, you go to XH, find the fit. That's this point right there. That's the YH hat. Okay. Your H is for here, because here we're interested in this point right here. Okay. Plus or minus, all of this now is our margin of error. Margin of error. Okay. It's a t number times the standard error, right? All of this stuff that's down in the bottom. Okay.
All right, so let's make let's use use the CARS data again. Make 98% confidence intervals for the mean response when x equals 4. Okay, as if you see a 4-year-old car, you want to estimate the mean response, the mean asking price, mean sales price. All right, so I'm just going to use that R code that I have there in the notes. I'm copying and pasting. Okay. First of all, I've got my B1 and B naught, my model coefficients there, and my fits and residuals. Okay. And SSE and MSE. Okay, sum of squared errors. It's just the sum of the squared errors or residuals. MSE, remember, it's just the sum of squared errors divided by its degrees of freedom, which is n minus 2. 10 minus 2 is 8. The standard error, I'm going to use that formula that's in the notes there, and it's when I fill all that stuff in, it's all that, right? Okay. Just copying this right out of the notes. Now I can go ahead and get my left endpoint for a 95% confidence interval. Thusly, okay, right. 4 is my value of interest there, right? The XH number. Here's my slope coefficient. B naught. Here's all of this stuff is my margin of error, right? The t number and the standard error here. Okay, and then to get the right interval endpoint, it's all the same stuff. It's all the same stuff. I just add that margin of error. And by the way, remember we're doing a 95% confidence interval here. If you're doing a 95% confidence interval, then you're looking for the 97.5th percentile. Remember, because you cut that 5% in half and put it on each tail. So you're looking for the middle 95%, but you're looking for the 95 plus half that 5%, which is 2.5%. 95 plus 2.5% is 97.5%. You're looking for that percentile. So your left and your right endpoints, as you could say, LPT and RPT, right? We can say that when you see a 4-year-old car, you can be 95% confident that the mean sales price is going to fall between this many $100 bills and that many $100 bills. Okay, if I wanted to make a 98% confidence interval, I do the same procedure. I just have to look for the 99th percentile, right? 99th percentile. So, and of course, this interval is going to be larger because the more confident you are, the larger interval you're gonna need. Remember, this interval only applies to when we're talking about an age of a vehicle of 4 years. Okay, if we change the x variable value or the xh variable value, that is, this confidence interval is going to shift. It's going to shift. Okay, now that's all more or less done by hand. Okay, I've done all this calculation stuff by hand with R in here. What if what you really want to be able to do, though, once you know a little bit of R, is actually do it with R. Let's do it from scratch with R. Okay, I'll put my age and price data in there like so, and I'll make a data frame. Data frame is just a certain kind of data structure. Okay, R uses different kinds. Data frames are very popular. They're sort of robust. You can put all kinds of things in there, categorical variables, quantitative variable values, all kinds of things, even different kinds of objects and columns. And it also uses matrices. There are a lot of different kinds of structures here, and depending on what kind of function you're using, you may need one structure over another, but there are ways to convert data frames to matrices and vice versa. But so we can anyway, we can put these two variables in a data frame to see what that looks like. It just looks like that. Okay, and okay, so now I'm gonna do a linear model for my data. Right, that's how I would do that real fast with R. I'm gonna create a set of new data. Okay, ND for new data. Okay, and we'll see why we want to get used to doing that in a lesson or two. But now I'm going to use this predict function. Okay, it takes the output from my linear model, which I've called out, and this new data, this ND, this could be just one value like we have here, or we could actually let it be an array of values. This will actually compute multiple confidence intervals at a time. So if we wanted to find, if we want to predict the mean response based on several different ages at a time, then we could let ND be actually a data frame of several values, and then it'll spit out all of those confidence intervals. But we have to, there's a subtlety there we want to talk about first when we get to inferences for or multiple confidence intervals when we talk about the Bonferroni procedure. But so more to come on that. But for now, let's just make one confidence interval for the mean response based on age of 4 years. The interval type is confidence. Okay, we'll make another kind of interval here in a few minutes. My confidence level is a 95% one, and bang, there it is. Okay, it's a heck of a lot easier, isn't it? I could then, if I want to make a 98% confidence interval, do it like that. Just set my confidence level to 98%. You see that we get the same as what we got previously.